Good morning. Welcome to Krishna's classroom. In this talk, we look at two structural theorems, and the conclusions are almost everywhere conclusion. Now, this is the significance of that because we have introduced the concept of sets of measure 0, and then many results have been concluded with almost everywhere property. The property is valid almost everywhere. Now, here we have two results of that kind, and this is the theme of our talk. So, let us look at this here. So, let me state the theorem. The first theorem I want to take up is suppose mu of x is finite. Now, we are working in x mu. We assume that this is a complete measure space. Okay. Now, let x be such that and mu be such that mu x is finite. And this is crucial. The second condition that we assume is this. There is a function f which belongs to L1 mu. Let S be a subset of the complex plane where S is closed. S is closed. And the averages AE over the measurable set E of F defined as 1 upon mu of E d mu lie in S for every E belonging to the measurable, the sigma algebra with mu of E positive. So that this is well defined. The average is well defined. Okay. I'll just explain what exactly this means. Now we are assuming that this particular average that you compute lies in S, where S is a closed subspace that we have of a closed subset of C for every M in the sigma algebra with mu of E is positive. Now these are the assumptions. Then we conclude that f of x almost all x belonging to so what we conclude is that the fx should be the value, the function f should be mapped into S for almost all x belonging to x. That means except possibly on a set of measure 0. Okay, fx belongs to x for every x belonging to x. Now this is the conclusion. Okay, now let us try to understand this result. So the best way to understand any theorem is to take a very simple, manageable example and see what it means in that case. So let us look at that. So we'll take the case of one dimension. Okay, so x you take as some closed interval A. Okay, so that, and mu as now m measurable sets and what you take mu as a limit. Oh yes, this is x m mu. So what we look at is a function. Okay, let me see what is the average. Okay, so we are taking f from x, that is okay. So you have some interval AB here. This is the domain, and then this is the range. So what you have is, let us take, in the example I take the function to be non-negative and so on. So it does not matter in this case. So what you have is this. So you take a function whose graph is something like this. I am taking a continuous. Then you know that any point in AB gets mapped somewhere. What we assert is the following. Now suppose you take another a subset of this. Let us take an interval. Need not be an interval. Can be any limit set. And you know that the total measure of the interval AB, that is measure of x, equal to b minus. Okay. Now let us take some e which is equal to the interval CD contained in A. So let us take this interval CD. Now you see that where does this get mapped to? Now you see that the CD gets mapped to, this is the portion to which it gets mapped. Okay, let me mark that out. So this is what you have. Gets mapped to this part. This is the part which it gets mapped. Fine. So okay. Now what do we have? The length of this interval is mu of Now what we are computing is this integral 1 by mu e integral over e fd equal to mu e is minus c d minus c integral over c to d of fd. What is that? So this is of course the area. This is actually the area. This is the area. Okay, so integral c to d now we are dividing it by c minus t. Now you see this is an irregular region whose area is something, I mean whatever it is. Now you see that what we are looking at is the average of this. So 1 by, okay, what is delta E? Delta E is then the some number, okay, some height this height is delta E, so that you have delta E times d minus c equal to integral c to d this is what you have. This is what you have. So you are finding a value here which is designated by delta E. That is the average of f on this. Not delta E, I am sorry. This is AE. Sorry, this is AEF. So this is AE. This is AE. Okay. So this is the average that you have. This is the average. So average into the, or you are, what you are doing is you are approximating this irregular area by a rectangle, and you are seeking its height, and that height is, this is what you call AEF. What we assert is that this AEF would also lie in the particular S contained in C. Okay, for almost all x. Now actually you can see that suppose you just modify this function at some point here and keep it outside here. So maybe even assign a value infinity. So it is not going to be in any closed set. Okay, but so what you can say is you cannot assert that for all x lying in the interval CD, fx will be finite, because there are some places where it goes out. Okay, so that does not affect the statement, because we are making a cautious statement that fx belongs to S for almost all x belonging to x. Okay, so what we are doing is we have a sort of averages. What are these? For each subset of AB, for each subset E of AB, where E is measurable, not necessarily an interval, is measurable, Lebesgue measurable, we can compute this. Now all these things will go into some particular S. Now what we are asserting is that in fact Fx also for every x on the interval AB will be lying in that closed set almost everywhere. So it's a cautious statement. It is almost everywhere. That means maybe on a set of measure 0, this may just violate this statement that we have said. But it will happen only on a set of measure 0. So this is the statement. Now let me just briefly recall. Now we have started with a CD, which is E. It's an arbitrary subset. Here we are taking as an interval. And now we have computed the average. The average is 1 by mu E integral E f d into. That's equal to 1 upon d minus c integral c to d f d. Okay, so this is the average. Now the average would certainly be something, that's lying here. So you have for each subset E, measurable subset E, we are taking the average, and then it goes into some closed subset. What we assert is that for all x belonging to AB, Fx also belong to this particular S for almost all x. Now that's the statement. So if you have analyze this example, it will be clear what exactly you are talking about. And you see that when you talk about the average, you are looking at the height possibly, so that this regular area is now replaced by a rectangular, a rectangle whose height is what you call AEF. Okay, so I think it must be pretty clear. Now we can go to proving this result. Okay, one more thing I want to say. Suppose it's not necessarily on a set of measure 0, this exceeds. Okay, suppose Fx does not belong to S on a subset E whose measure, what is that, with mu of E positive. It's a positive measure. Okay. Now what is that you can do? See, Fx does not belong to S. It just falls outside that. Okay, right? So let us assume that Fx is, so let us assume that S is some closed interval within some closed subset. Therefore, outside that, this is happening. And in that case, what happens? Okay, then I'll just complete the statement here. Then what we see is that 1 by mu E integral over E Fx dx, that is the average of F on E, does not belong to S. We are assuming Fx is not in S, therefore for all x, Fx is outside this, and therefore this does not belong to S. Okay. right? So that is what happens. So we are just making this statement. If we were, so that also indicates possibly proof of this theorem. Now let me try to prove this. So that's the example we have analyzed. And my suggestion to the students is that whenever you have a theorem stated, okay, whenever you have a theorem stated, go to a simple but non-trivial example and then examine what the theorem says on that non-trivial example and get a feeling for the statement of the theorem. Check the given conditions, that is the data, and then conclusion, and see how they are related in the case of the example that here you have considered. And that should give you some insight into how you prove this theorem. Okay? Right? It doesn't mean that a theorem stated or a statement given is true for some example, then you cannot conclude that the statement is universally valid. That's a different thing. But we are taking a situation where there is a proven theorem which you want to analyze, then this is the case. Now what more you have, that also suggests to you the path through which you have arrived at the generalization. Okay, it is from this analysis, from this particular example that we have analyzed, and you got the feeling, and now you try to generalize. Okay, so as you can compare with whatever I said, this particular example, compare it with the general statement of the theorem. So let us look at the proof of this. So what we have is this. This is your x, and this is the complex. We are talking about complex value. Now you see, to take a closed subset, not any closed subset, S is closed, and we assume that all the averages for every measurable subset so E is, and then you see that this is, so the average AE, because F is from here to the complex state. Okay. Need not be for every x this goes, but what you can say assert is that, so look at this AEF. AEF turns out it is, I have chosen an arbitrary element of M. Okay. And then this is the scenario that, so these are the assumptions that we, then what we assert is that F maps every x here. Okay. Every x here into S for almost all x. Okay, put it that way. So for almost all x in, for almost This is the conclusion that we. Okay, what we are assuming is the averages are always inside this. Then for almost all x, so you just compare with the example that we have discussed earlier. Now, what is the strategy? The strategy is this: S is therefore S complement in C. Now, what you have is S complement is the union of countably many disks is delta of the type. So this is with set of all z down to C with mod z minus alpha is less than alpha belongs to alpha what is called S complement, and this delta is contained in this complement. So alpha is the center of the disk. Alpha is the center of the disk. So let us assume that suppose this is the disk. This is alpha and the distance is r. Okay. So what we look at or what we infer immediately is that the distance from, that is distance from alpha to any z is greater than r for every z belonging to S, because S falls outside that, to see that there is some positive distance between this delta and this is your delta and this S. Okay, so this is the conclusion that we have, right? So that's what we do, and there's a positive distance. Now let us work on it. So our strategy is this, the following. We take F inverse of E. F inverse of E F inverse of delta. So let us take F inverse of delta. Now F inverse of delta let F inverse of delta be designated by E tilde. Okay. Then we claim f of, or what you call the measure of what does this mean? F inverse of delta equal to E tilde. F inverse of delta equal to E tilde implies, or this means that delta is equal to f of E. This is the meaning, or equal to, right? F of E equal to delta. So what we are asserting is that what we are asserting is that E tilde has its measure 0. That means a set of points which go into delta, and delta is arbitrarily chosen, okay, for any delta which lies outside S has measure 0. So our claim is that E of E tilde 0. Let us see how we prove. This is a very simple one. Now, if mu of E by quantity, suppose mu of E tilde is positive, then what do we have? We arrive at a contradiction. Compute this. A E tilde minus alpha. This is equal to 1 upon mu of E tilde into integral E f minus alpha. This is it. That is the distance of the average from alpha, okay, is given by. Now what you can assert is that this is less than or equal to 1 upon mu of E tilde integral over E tilde And what can you say about this? See, because fx is in S and alpha is here. So the distance between if fx is in S, then mod f minus alpha greater than. But what do we have here? See, this by our original assumption is less than or equal to R. Okay? Because AEF minus alpha and is less than or equal to R. But fx belongs to S implies this is greater than R. Therefore, this is impossible. This is because you see that mod f minus alpha is greater than or equal to R. then you are integrating over E tilde. So essentially, it is sorry, is less than or equal to R. Therefore, it is equal to R times the measure of this one. Okay, and we have divided by that. Therefore, this is R. That's how it comes. And therefore, what does this mean? This implies mod f minus alpha is actually greater than R. So there is a contradiction. Okay, this is impossible. What does this mean? This means mu of E tilde What is E tilde? E tilde we have already worked out. Okay, right? So what do we have? This means that this implies f of x belongs to S for almost we have worked with an arbitrary disk, and then the S complement can be written as the union of countable of such disk. For each disk you can. Okay, therefore this is the conclusion. Okay, so that completes the proof of this. Okay, so we take up another result of a similar type. Take the theorem. Let EK be a sequence of measurable x. That means they all belong to sigma algebra. Assume that finite. This is a section that then for almost all x lie in at most finitely many of the sets so you take any x belonging to x, it can lie only in at most finitely. It cannot lie in infinitely many of the EKs. right? And that is the case. It's an almost everywhere. What we are asserting is that for almost all x. Let's prove this result. So let us. So what we are asserting is that the set of all x for which lie in infinitely many of the sets Ek is a set of measure 0. Okay. So we assert that the set of all points x which lie this is the meaning of the statement. We are not saying that such points do not exist, but such points do exist, may exist, but the set of all the such points has measure 0. So let us prove this. So let us designate such a set as this is the x for which then we claim mu of A let us work on this. So what we do is we define an f through which you test the whole thing. Okay, right? The characteristic function of what does this mean? If x belongs to Ek, then Gx equal to 1 there. Okay. Otherwise, outside it is not. Okay. So if x belongs to some finitely many Ek, then Gx is well defined. Okay. Corresponding to each such Ek, you get a 1. So let us recall for each x belongs to x. Each term of either 0 or 1. Hence, x belongs to K if and only if infinity. Because x belongs to infinitely many pk's, therefore this is gx is going to be infinity. Okay. Now let us compute integral over x g d mu. This is essentially the sum in sigma k equal to 1 to infinity mu of it. And this we know is finite. This is finite. This part is given. Okay. But this part is going to be infinity. Okay. Therefore, you see that these are not compatible. Okay. Hence, that is such a G belongs to L1 mu okay. So such a G belongs to L1 mu, and so Gx is finite almost everywhere. Okay. So this is the conclusion that okay, that's our so that completes the proof of the theorem. Okay, with this I conclude one chapter, and we okay. So we conclude this chapter, and we start with now looking at the problem from a different perspective. That means the integrals we are now going to look at as what are called functionals, in fact linear functions. Okay. And then connect the linear functionals with the functional. So that's our next task. So thank you very much.